Good afternoon, everybody, and welcome to another Geo-Institute live stream. It's been a little while, but we're back on the YouTube channel, ready to have a great time today as part of our summer of live. My name is Brad Keeler. I'm the director of the Geo-Institute, and we welcome you to the second of 3 live-streamed Cross-USA lecturers given by this year's Cross-USA lecturer. Good afternoon, everybody, and welcome in the series, Carlos Santamarina. If you don't know anything about the Geo-Institute, after you watch this today, you should, as a matter of duty, head over to geoinstitute.org, and there you will find out all kinds of things about us, including that we are a technical society with about 12,000 members, most of whom are geotechnical engineers and or geologists, and that we are part of the American Society of Civil Engineers. And as always, if you like what you see, and I feel like you will today, you should click a like, subscribe, and get notifications. And if you do those things, we'll let you know every time we post something to the YouTube channel. We have one final plea for you today. If you have not yet made your contribution to Geo-Institute student programs in 2026, it's a great time to do so. I mean, it's always a great time to do so. You can head to geoinstitute.org and click the link that says Student Participation Fund or something similar to that. You'll get a page where you can make your donation, and there are some incredible thank you gifts as well. And here in my hand, I have the Ralph Peck bobblehead. Wouldn't you love to have one of these on your shelf in your office or at your house to proudly display? 1, that you're a proud geotechnical engineer, and 2, that you made your contribution to GI student programs. We were founded in 1996, hence we have the 96 Club. You make a $96 contribution to student programs, you get one of these sent right to your door. We would love to be able to send it to you. Now, back to today's programming. The Cross USA lecture. Oh, actually, I did forget one very important thing. The Cross USA lecture is brought to you by our friends at GeoPeer, and we have a brief 35-ish second message that we're going to play you from GeoPeer as soon as I can get the thing going. My apologies. I was trying to go on the fly here. GeoPeer has been a sponsor of the Cross USA lecture for the past 6 years. We are very grateful for that. Thanks to their support. Thanks for their support from our friends at GeoPeer. Generous support of this lecture series. Now, our feature presentation. Here to introduce Carlos is one of the leaders from our Student Leadership Council. They are one of 3 groups, including the Local Involvement Committee and the Geo-Institute Board of Governors, who select the Cross USA lecturer every year from the nominations that we receive from the University of Colorado. It's Mode's show. Mode, thank you so much for doing this, and take it away.
Yeah. Thank you, Brad, for having me. So good afternoon, everyone, and welcome. My name is Mohammad Shoaib, and I am a Ph.D. student in geotechnical engineering at the University of Colorado, Boulder. I'm also a vice chair of GI Student Leadership Committee. It is my pleasure to serve as a moderator for today's Cross USA lecture about energy geotechnology. So on behalf of CU Boulder Geotechnical Group and Geo-Institute Student Organization, I would like to warmly welcome all of you and thank you for joining us today. So before introducing our lecture, I would like to briefly say a few words about the ASCE Geo-Institute Cross USA lecture. For those at the university who may not be familiar with the program, the Cross USA lecture is an initiative of ASCE Geo-Institute that brings distinguished geotechnical professionals to GI chapters and graduate student organizations across the United States. Each year, one distinguished lecturer is selected through a competitive nomination process. If you know someone who has made like outstanding contributions to our professions and would be an excellent speaker, I encourage you to nominate them. Nominations are typically due in February of each year, so please keep that in mind for the next year. So the GI Board of Governors selects the annual lecturer, and for the 2026 and 2027 lecture year, the selected cross-USA lecturer is Sissi Nicolou from National Institute of Standards and Technology, or NIST. For more information, you can visit the cross-USA lecture portal. The selected lecturer then travels to multiple host institutions across the country, sharing their expertise with the students, researchers, and practicing engineers. If you are involved with the Geo-Institute chapter or graduate student organization, I encourage you to consider applying to host a future cross-USA lecture. The Geo-Institute provides some financial support to help bring the lecturer to your institutions. And even if your group is not selected for sponsorship, it's still worth to reach out to the lecturer directly. So in today's lecture, the agenda we have, today's program is simple. The Professor Santamarina will first deliver his lecture. After the presentation, we will have some interactive question and answer session, which I will help to facilitate. Then we will conclude with a few closing remarks. So it is now my great pleasure to introduce today's speaker, Dr. Santamarina J. Carlos. Dr. Carlos is serving as a professor at Georgia Tech. He has held faculty appointments at New York University Polytechnic, the University of Waterloo, Georgia Tech, and the King Abdullah University of Science and Technology, Saudi Arabia. He earned his bachelor's degree from Universidad Nacional de Córdoba. I'm so sorry if I'm just pronounced wrongly. I'm really sorry. In Argentina, yeah. And his master's degree from University of Maryland, then his PhD in civil engineering from Purdue University. So his research integrates generally experimental and numerical approach to understand the behavior of geomaterials, including soil, sediments, fractured rocks, and complex fluid, with application in geotechnical engineering, energy geotechnology, geological carbon storage, and infrastructure resilience. So Professor Carlos has received many of the profession's highest honor, including 2024 Casagrande Lecture, 2022 Bishop Lecture, and 2014 Terzaghi Lecture, and many more. He's also the author of several influential books, top-notch journals, and conferences proceedings. So please join me in having a warm welcome to Professor J. Carlos.
Thank you. Thank you so much. You were very generous, Mother, with your comments. Let me try to share my screen. I have to go to Windows, and it will be. Please confirm that you can see my video, my screen. Is it okay?
Yes,
great.
Excellent, wonderful. So here we go. Colleagues, what a pleasure to be here once again with you as part of this series of conversations. These are not real lectures. These are, in the spirit that I'm trying to bring, is conversations to assess where do we stand in the profession, and not so much to do it retrospectively, but to project our community forward. In this context, the theme is the energy geotechnology field and our potential role. Look, we are all fully aware of what goes on in the world, from the heat waves that are creating chaos in Europe to the Strait of Hormuz, and now it's part of our common geography. The deadly headlines remind us of the critical role of energy in our lives and the important implications of livability for ourselves and future generations. So today, my goal is to try to disentangle this complexity of all the energy problems and as well as the wording that comes behind that sometimes can get so confusing, and then to touch on few items where the engineering community, our engineering community, geotechnical engineers, can become involved to be part of the solution. So This is a little bit of history here. This is not something new. Throughout the 20th century, our community has been involved in building all the dams, offshore foundations, and you can find Terzaghi's and ranking lectures on these topics throughout the 20th century, involving geothermal systems, nuclear waste disposal, mining. But what happens in the last 25 years, since the beginning of this century, is that now certain things have become catalysts, nucleators. And one of them in particular is the fact that all these processes, thermo, hydro, chemomechanical, are coupled and they are intimately involved in energy systems. From nuclear waste to underground energy storage to CO2 geological storage, the implications of induced seismicity, the potential of energy storage in the subsurface with implications of repetitive cycles of all kinds. So that is a significant development that has taken place, let's say, in this century. And furthermore, in the last 10 years, this is becoming almost formalized as a subdiscipline of our field. We see university programs hiring faculty. We are updating our curricula and including these themes within our courses and providing new courses. We have a new, very effective, very dynamic committee in the International Society, the TC 308. We have journals that have been created within our community to address these issues, but also articles throughout the classical journals are increasingly addressing energy-related issues, and of course, those coming from the earth sciences. In summary, what I think that is going on is that we are changing our state of mind from thinking of soils, rocks, and water as construction materials and then good to support our infrastructure, to all of a sudden we are thinking of soils, fractured rocks, energy fluids of all kinds, which are components, intimate components of energy systems. And so today the presentation is split in two parts. The first one is, and it takes about half of the time, we will look into the energy situation worldwide, because I have been trying to clean this up because I hear so many stories coming from all sides that gets really quite confusing and misleading. So we will try to identify a few myths, facts, paradoxes that are behind. The second part, it will sound more geotech. So here we go. Why is energy so important? Well, it controls quality of life. And in fact, if we plot quality of life versus power consumption, it follows a trend. And not only that, if we track each dot here being a different country around the world, if we track how these dots have been evolving during the last 50 years, quality of life has increased significantly. Look at the UN goals. They have been very successfully accomplished in this regard. But that has happened. Quality of life has improved at the expense of increasing power consumption. And that is interesting and challenging. So, for example, in the US, with already very high quality of life in the last 20 years, the power consumption hasn't increased very much, but China has doubled the power consumption per capita in the last 20 years. In the meantime, the US has maintained the good life expectancy. Some oscillations here may reflect COVID effects. However, China has seen a very significant, dramatic increase in life expectancy because of increased quality of life. But we cannot sustain this trend, so we have to all think, how are we going to contribute to maintaining the quality of life in our developed countries while decreasing the power consumption and allowing the developing world and supporting the developing world to increase quality of life, but not doing the way we did it, to do it while maintaining low power consumption. And somewhere in that mixture, we are going to identify a long-term sustainable energy system. Really, we have to become involved on both ends. Now, you may have heard a lot about the incredible dramatic developments in solar panels, for example, and China taking the lead. And in fact, the efficiency has doubled or tripled in the last couple of decades. But all the advances in renewable energy have not even offset the increase in total power consumption. So indeed, when we look at it percentage-wise, right now we depend 82% on fossil fuels. By 2050, we are still going to depend 70% on fossil fuels. And while there has been a very significant increase, actually, by 2050, we are going to be consuming more fossil fuels than ever before. In part, why are fossil fuels so important, in particular petroleum, as we have come across in the last few months? Well, the whole transportation system is based on oil and gas. 90% of the transportation system or more runs on oil. And by the way, the rejected energy tell us that how much of the energy went in 28, 22 got rejected. In other words, went to waste. This is the most inefficient component of the energy system, yet is consuming all our oil and is the greatest generator of CO2 emissions. And transportation is us. I mean, except for the vehicles, but the transportation network, the system, etc., is us. We ought to have an important role to play, us being, in this case, civil engineering. And yes, we have become intimately familiar with the Strait of Hormuz, which hasn't affected us so much because the US is the largest oil and gas producer in the world, but it has had dramatic effects, for example, in all South Asia and in Europe, etc., because that is a choke point for 22% of all the oil and gas that gets consumed in the world, which is 100 million barrels a day. 22 million barrels go through the Strait of Hormuz. And Saudi Arabia has long anticipated this, so it has built a pipeline that crosses from east to west to Yanbu. And we have been involved in studies related to that, for example, corrosion, a major geotechnical problem, corrosion of buried metals. But Saudi Arabia has been able to mobilize something like 7 million barrels through the Red Sea because of this infrastructure. Now, we are so dependent on oil and gas, gasoline for our transportation system. Does that need to be the case? Well, first of all, let's realize that there is so much energy in storing the chemical bonds of gasoline that is so difficult to replace. For example, the best batteries in the best electric vehicles today are about 100 kilowatt hour batteries, which actually is like 10 liters of gasoline. But by the time it gets delivered to the wheels, stored electric energy is more efficient than gasoline. So actually the 100 kilowatt hour battery becomes about 38 liters of gasoline, 10 gallons. However, that battery weighs 1,500 pounds. And it has a certain life, limited life, etc. Now, there are alternatives. And there are lots of ultra high efficient vehicles. Even Volkswagen delivered this one 25 years ago, and it could do 100 kilometers per liter. In the units here we use in the US, that is 235 miles per gallon. Folks, imagine if we were all commuting with this car today, the whole energy situation would be totally different. The technology exists. Is whether we choose to embrace it or not. And this is just one of multiple examples. But the consequences are very profound. In fact, because of cheap oil throughout the 21st century, the cities in the US grew very large, and we went to suburbia to enjoy the benefits of being far from downtown. And this is the city of Atlanta. And today in Atlanta, we commute every day the distance from the Earth to the sun. And most of those vehicles have a single occupancy, and they are not efficient vehicles. Just imagine if we make use of the technology that already exists. We're not looking for revolutions. And we're not going to change the urban development because the cost of the existing infrastructure on all our homes, etc., is very expensive. The change has to come through the transportation system and our highways and connection systems. To put some numbers in perspective, it's good to have few simple rules. For every mass, let's say kilogram or pound of fossil fuel, we emit 3 times higher mass of CO2. Why? Because the oxygen atom is heavy. And so when you combine oxygen with carbon, it becomes very heavy. So think of 1 pound of gasoline, 3 pounds of CO2. And that's what we are emitting in the transportation system when we make concrete, because we are using fossil fuels in the kilns. And furthermore, calcium carbonate gets decomposed and sends CO2, concrete being the second highest emitter of CO2, heating and cooling of our homes and systems, and mining very inefficient, as I will tell you soon. All these are classical civil geotechnical issues, which are at the top of the line, on which we have an opportunity to make a difference. Another rule of thumb that I would like to share with you follows. This is the size of the world economy per year, $110 trillion. We consume 172 tera kilowatt hours, or trillion, 10 to the 12 kilowatt hours of energy. And we emit worldwide 37 tera kilograms of CO2. I know that these are not the standard units that you may have found in the literature, but it allows me to do a very nice relationship. If I divide everything by 110 tera, I get that for $1 of money that I use in the economy, I'm actually consuming 1.6 kilowatt hours of energy, and I'm emitting 340 grams of CO2, almost a pound of CO2. So next time you're going to buy an ice cream or a car just think of this relationship. That dollar goes through the economic system and it relates to almost a pound of CO2. The other thought is that all these are tera quantities, 10 to the 12. So this is a huge problem. This is a tera problem. We really need to begin building up multiple solutions to come up with a tera solution. And the other thing is that this is a very simple rule that you can use to check concepts every minute, from your federal government to your state to your home scale. And because if you use complex models, it is easy to reinforce our prior beliefs. For example, in the discussion between electric vehicles and internal combustion engine vehicles, you see reports coming from our national labs reaching different conclusions, diametrically different conclusions. So go ahead and keep an eye on that rule, because it will be quite powerful. The other issue we have in all this analysis is, where do we draw the boundary? For example, there are a large number of cities that have promised to be carbon neutral by 2050. Folks, the only thing that may be carbon neutral, maybe the lights will run on solar, but all the salaries that the cities pay to the employees will take it home, and because our economy is fossil fuel based, they will burn it in fossil fuels, and they will produce emissions. So the cities, when they say that they're going to be carbon neutral, they choose to circumscribe that, to limit that to a very narrow domain, which actually is not being shared with us. Let's be careful with that. Another one that I find quite annoying, because I cannot turn it off, is this auto restart feature that the car shuts off and then restarts again. So this is a snapshot of my car a couple of years ago. It was quite new, and it had started 100 times. It has been off by 27 minutes and saved 0.14 of a gallon. But that car needs a much better starter, much higher quality starter, a much better alternator and the whole control circuitry, and a much better battery that is 3 or 4 times more expensive. If I would take all that money and I convert it with that rule, it is not so obvious that there is any benefit in this feature. So let me encourage you to remain skeptical. There are some solutions that are not solutions that will worsen the problem. Another case in point is, where do we draw the boundaries for the analysis? You may see numbers like this as to what is the life cycle cost of different energy sources from cents per kilowatt hour. Nuclear is not doing well at all, and but solar and wind are doing very well. But if you do the gas and the coal and you add the cost of carbon capture and storage, it jumps quite significantly. Probably it may even double the cost. And if you consider the fact that the solar panels and the wind turbines are not lasting as long as they were planned to last, and they're being replaced with 8 to 10 years. And furthermore, they're working only 20% of the time, which is called the capacity factor. This is something I learned from Nathaniel Bolson recently. All of a sudden, these numbers become increasingly higher than is being portrayed. What are the real numbers? Because if we don't know the real numbers, the proper techno-economical optimization falls through. Now, we're hearing, and the evidence is showing that sea level rise is taking place. There will be almost a foot, it will be a foot higher by 2050, and 3 to 4 feet higher by the end of the century. In the meantime, in the US and in the world, the numbers are very similar. 40% of the population lives in coastal areas. And now you can go into NOAA and ask these flooding maps, you set the elevation, etc., and you will see how our cities will flood and the cost of that. And of course, there should be New Orleans somewhere there. What are we going to do? Coastal geotech, probably one of the most fascinating subdisciplines growing within our field, and it is critical, and we need to adapt our cities, our environment to changing conditions. It will be very difficult to fight them with additional infrastructure per se. Now, there are good news, and I would like to put all this in a positive spin. Population growth is rapidly decreasing. I was reading recently there are more dogs than children in Japan. And the whole world is really going down below the 2.1, which is children per woman, which is what is required to maintain the population, a little above 0.1, a little above 2 because of life expectancy, infant mortality rate, etc. But this has been dramatic. And even Africa, which started at the beginning of the last century with 6-7 children per woman, now is decreasing rapidly. And by the end of the century, we will be finally beginning to decrease our total population. But before it begins decreasing, we will reach about 11 million with lots of old people, because life expectancy is increasing worldwide. Another good news is that the sun is shining, and where it shines the most is where some of the greatest problems are and deficiencies are today, typically where the population growth is higher and with increased quality of life, and there is a positive feedback decreasing the rate of population growth, and with women's education, city life, etc. And so solar is really going to be a leapfrog technology for the world. Another good news is the fact that nature has been capturing the CO2 fed fuel by solar energy. And a tree, by the time, within 40 years, will probably offset about 1 ton of CO2. And you can do this analysis starting with the carbon molecules in organic matter, etc. And you convince yourselves that to offset the actual CO2 emissions, we will need to have about 1 trillion trees, a tera number of trees. Once again, the tera is pervasive throughout, to offset most of the CO2. By the way, I did the computations of how much a geotechnical engineer makes and will make through a 40-year professional career. And to offset my life as a civilist geotechnical engineering, I should have 3 acres of dense forest. keep that as a number when you try to do some rough back of the envelope computations. The Trump administration, in fact, during the first cycle, did start the executive order to 1 billion trees. And but that is really, which is great, but that is really a very small quantity. Will occupy less than 0.3% of what is today the USA farmland. By the way, there are several trillion tree initiatives worldwide that we can contribute to. Furthermore, wood is a great construction material, and it could also be a sustainable biofuel in the sense that it grows, we burn it, we emit the CO2, new trees will capture it, and so it can make it a little bit more sustainable. Now, many changes are taking place, and this is another one. I'm trying to check the times. Bill Gates, who has been very active in the climate discussions. Now he was quite criticized for his letter in October 2025, where he kind of changed the tune. And what is beginning to perceive worldwide is that it will be very difficult to stop the momentum that we have right now in realistic terms. We are not giving up, but in the meantime, let's begin adapting. And that is a theme that was very strong in the COP, where all countries get together every year around November. And the last one was in Brazil. Adaptation, resilience, forests, increased renewables, industry decarbonization were key topics. So the theme is changing, facing the reality that we encounter today. Two more slides on this first part. The one is that there are a few misleading themes. Carbon neutral, let's forget about it. Net zero 2050, let's forget about it. Circular carbon economy is thermodynamic impossible, so let's don't even use it. Let's recognize that because we depend on fossil fuels so much, the transition out of fossil fuels will be fueled by fossil fuels. So indeed, we're going to increase consumption of fossil fuels in the foreseeable future, in the next couple of decades, for sure. Now, there are some paradoxes. If one country decides to get stricter on climate policies, industries may go somewhere else. And so we haven't solved the worldwide problem. Furthermore, if fossil fuel producers recognize that there will be changes in regulation that will be tough, they will start accelerating extraction. That is called the green paradox. Rebound effects. Now that the systems are getting more efficient, let's use more of it. That is not good, right? I mean, I have to recognize that I see more LED lights on around my house at night than lights before, because now LEDs are more efficient, but all of a sudden we're using many more of them. And furthermore, if we save money, what would we use the money for? Because ultimately everything, every ultimate use will end up in fossil fuels unless we plant trees. Finally, I have begun recognizing different attitudes in individuals and myself. Some of them are like an ostrich. They prefer not to even look at it. Some of them are optimists. Technology will solve it, will be okay, blindly. Some of them are charlatans. They are selling us fake technologies. Let's be very careful with them, because that will derail the future of our children. We see the greedy. We have very smart people in our communities and in this field that are quite apocalyptic. And they do know the data and they do know the physics, and we should listen to them. But I think that we are engineers, we are problem solvers. Let's get involved and let's solve it. Let's get involved not only as engineers, but also in leadership roles. There are only 2 out of 100 in the Senate and 12 out of 435 Congress people with engineering and science background. All the others have background in international politics, relationships, law. Let's get involved. We are the problem solvers. We're going to move on to part 2, the energy technology, because we need to do things. So what can we do? And this is a field that has been growing in our minds as time passes by. We started recognizing what are the different fuels, the fossil fuels, the renewables, nuclear, and some of the geotechnical opportunities. Then we recognized that we had to pay more attention to mining. Of course, mining has always been part of our system, but now the critical minerals have become increasingly more critical. And conservation and efficiency within our field has been going around reminding us. And more recently, we hear a lot about hydrogen. And as I said earlier, the need for adaptation, particularly in coastal communities. So this is it. This is the energy geotechnical engineering field in 2026. What can we do? Where can we participate? So we're going to go one by one, and I'm just going to show you a little example, a very simple along the way, and I'm just going to highlight a few topics. The first one is to say we have enough oils for the next 50 years based on proven reserves. There is a possibility that goes beyond that, but let's say 50 years. We should be out of the energy transition by then, by the way, we hope. But that oil is becoming increasingly more difficult to extract. It's not the oil that it was flowing out of the ground in Southern California or in Venezuela. We're going into deep formations beneath creeping salt, etc. And some of it is very viscous. We have produced pretty much half of all the proven reserves. We have consumed 1.6, there will be 1.7 terabarrels left. Now, this is an interesting fact. Our average recovery is only 35%. If we would use more effective enhanced oil recovery, we could reach 60%, but we still leave lots of the oil behind. And it's all about unsaturated soil behavior. It's all about capillarity, and the surface tension that you see on that spider walking on water, or the contact angle that you see on that water droplet on the lotus leaf. If we would figure out, please listen to this number, if we would figure out how to recover 1% of the residual oil, it would have about $3 trillion impact today. So this is migrating a little bit and expanding our framework of unsaturated soil behavior. And it's not so much Bishop effective stress, it's much more on the relative permeabilities into enhanced soil recovery. And to do that, we are exploring different things. How can we change those properties? So there are nanoparticles on this water, and as it contracts, now you see that it collapses, not a nice capillary bubble that was shrinking, but now it buckles like a shell. And if we put, let's say, detergent on water, without it, nothing happens. But if you do it, you decrease the surface tension so effectively that it breaks the surface tension. That's called Marangoni effect. And these are just two examples of wonderful opportunities in augmenting our understanding of unsaturated soil behavior to these issues. What about with gas? Well, it appears, and by the way, you can begin recognizing some of the names here: Iran, Qatar, Russia, and us. And so when we read the news, all these names are floating, and there are geopolitical drivers behind. We have about 60 years based on the proven reserves, and probably it's more than that. So once again, it's not very critical in the short term, and that is without including gas hydrates. And this has been truly a revolution, without hesitation. In the last 20 years, the energy situation in this country has been completely overturned because primarily of shale gas. Look, this is the Eagle Ford formation. At the beginning of 2010, there were just a few wells. 6 years later, there were 18,000 wells, and today, 2026, I just checked, the number still remains about 25,000 wells producing primarily gas, but some oil as well. You pick this up looking at satellite images. You see the light, and if you see satellite images during the day, you see all the paths where these are sitting. This has been revolutionary. Now, let me explain what we are actually doing. We are getting gas molecules, methane, from pores which are, let's say, 20,000 times smaller than the diameter of a hair. 20,000 times. The gas molecule has to migrate, and it's not the standard flow regimes that we recognize. It's another bouncing regime. And so that creates lots of difficulties, and that requires fracking. And in any case, within the first 3 to 5 years, these wells are producing somewhere between 50 and 80% of all the ultimate recovery. So don't think that this is an amazing resource forever. What about coal? Coal has a bad reputation because of its contamination and all the mining effects. But we have more than 100 years of coal for sure. And when Germany decided to shut down the nuclear power plants, it had to go back to coal. And many countries are going back to coal because of the war with Iran. And so coal is here to stay. I hope we make it better to make it less environmentally impactful. But this is a highly geotechnical problem, from stability of the mine to what do we do with the fly ash, to repurposing mines. And Dr. Akhdari at the West Virginia University is exploring that. To the environmental impact. These are strong geotechnical problems that are still very much in our field. There are 770 coal ash impoundments in the US. 44 of them have been classified as high hazard, and most of them have produced subsurface water contamination. And this is fly ash. When the coal burns, the little pieces of metal that did not melt, and they form these bubbles like Christmas tree balls that are hollow inside cenospheres, and they have very unique properties. And one of those properties that we should be quite alert is the fact that once they are in contact with water, and here we are measuring with Bender elements how the shear wave velocity evolves at no excess pore pressure. This is constant effective stress. As it gets older and as it ages and diagenesis takes place, within 2 weeks, 3 weeks, the shear wave velocity has increased dramatically. You see the travel time has shortened a lot. And so this material is actually developing some form of light cementation, which is going to hinder subsequent stabilization and consolidation. We have to be very alert. These materials can be very brittle, as past failures show. What about carbon geological storage? A couple of highlights. There is no low-cost scalable technology to capture CO2. And in my presentation in 2014, I put the number. There were 398 parts per million. Now we are at 428. It's going up 2 to 3 parts per million per year. Apparently, we should be very scared of reaching 550, which at 3, we are only 40 years away, 40, 50 years away. Furthermore, if you do the whole analysis of the cost of capturing, pressurizing, compressing, transporting, injecting, it will be about the same cost as getting the oil to begin with. So this is going to be costly. How long should we keep it down in the ground? Probably 100 years, 200 years to say the least. We have to go through the energy transition. Then if it gradually leaks up again, energy will handle it. Is that right now we are exceeding energy's capacity to rebalance the equation. And storing it is a highly hydrochemomechanically coupled process. which gives rise to the performance of sealing layers. Quite a fascinating problem. There are many places where we have thought of where to store it. In the US, there are the Geological Survey and NETLA, if I recall correctly, they have made maps. There is plenty of storage capacity in the US. Mineralization has gained lots of relevance because the idea is that if it goes in, reacts with the rock and forms new minerals, then it will be very stable. It will not leak back. And probably the most successful project is in Iceland, Carbfix, Wallula in the state of Washington. There is a project in Oman. Recently, my colleagues in KAUST published a paper in Nature reporting a project in Zizan. And here is a demonstration. We put a piece of basalt. These are mafic rocks. And so that means that they have calcium, magnesium, iron silicates. The water with CO2 comes in, dissolves these silicates, and the water with the CO2 reacts with this and form precipitates calcium, magnesium, iron carbonates, which is the mineralization. These are the needles. These needles are aragonite from a simple experiment to make the point. Geothermal. Geothermal, I like this one, but more than I used to probably. Look at this number. Just take the geothermal gradient and compute what is it, 20, 30 degrees per 1,000 kilometers, and compute the temperature in the Earth, and you will convince yourself that 98% of the volume of the mass of the Earth is hotter than 1,000 degrees Celsius. There is so much geothermal energy beneath our feet, and very little of it is exploited, in fact, because of the challenges in drilling. How do we case it? The stability of proppants. There are projects now, if you follow the Department of Energy, trying to understand these systems under very high pressure and temperature, let's say 20 megapascals and 400 degrees Celsius, beyond the supercritical value of water. How will rocks behave? And what about the ductility of rocks? If you create fractures, how will you do that? In the meantime, our community has been quite involved with shallow ground source heat pumps, which are really quite wonderful. And I think that the key here is that we need to figure out how to install them fast, with minimal disruption to our homes, and at low cost. And then I think that we'll be more successful at embracing at the mass scale this technology. Wonderful problems related to transmissivity in fractured rocks at high pressure and temperature. And what happens when water goes into these fractured rocks in geothermal reservoirs? It dissolves the rock at the entry. By the time it's exiting, probably it's going through phase transformation, and it will drop all these ions along the way. So there is dissolution at the entrance. There will be precipitation somewhere else. Once again, hydrochemo mechanically coupled process, thermal. Hydrogen is something that everybody's talking about, almost in a dream fashion. It would be great if there is plenty coming out from somewhere in nature. There is some evidence that it does. We ourselves have been able to detect it here in the Piedmont. The quantities are really very small. The possibility of actually injecting water and producing hydrogen by serpentinization at great depth is being explored. In the meantime, we are producing hydrogen mostly by consuming fossil fuels. So hydrogen then is not an energy resource, it's an energy carrier. Like electrons are energy carriers. We burn coal or oil or gas in the Midwest. We transmit it through the grid, and we receive it as electrons in New York. Is that what we really want to do with hydrogen? And one of the challenges with hydrogen is that, well, first of all, the advantage is that it has a huge energy density per gram. To compare, is 4 times greater than methane. The problem is that hydrogen molecules hate each other, so it's very difficult to compress them. So if you compress it to 1 megapascal, 100 meters beneath the water table, 100 meters is 1 megapascal of fluid pressure, the density would still be more than 1,000 times lower than water. It's very difficult to compress hydrogen, which makes it the energy density per volume is very low. Furthermore, the molecule is little, likes to escape, there's fugacity and brittles, pipelines, etc. So that's the reason why people are exploring, for example, ammonia, but there are possibilities and challenges along the way. Nuclear is in a revival mode. If you just look at the uranium in minerals onshore, we have at least 100 years, and if we go with the seawater, it's very difficult to recover because it has a very low concentration, but then we have thousands of years. Now, here is the challenge, which is intimately related to us. There is no nuclear waste repository in operation in the world. Probably the closest is Finland's Onkalo, which was supposed to come on board 4 or 5 years ago, and every year is postponed. Now they are promising finishing all the documentation by the end of this year. But to summarize, all the fossil fuel still remains locally stored at the plants. And it is a scary proposition, even though the record is surprisingly good. Now, once again, following DOE initiatives, you see that bentonite remains a critical component. And in this, for the ultimate storage surrounded by bentonite, but this is intimately a thermo, hydro, chemo, mechanical, and even biological coupled process. And nowadays, the greatest challenges are what happens when, if the containers corrode and those compounds come out, corrosion compounds, and from the uranium come out, how will they react with the bentonite? Or what about if we dispose earlier so we don't keep it above ground, but that will create higher temperature? How high temperature can the bentonite take? And radiation will be very high. What will be the performance of bentonite after very high radiation doses? And there are several studies related to these topics. As we are approaching the end of the presentation, I would like to say that energy storage will play a critical role. I didn't address some of the other topics, like, for example, solar and wind. Wind, we can have a role in foundations, but probably our role in solar is much smaller, except that we may want to store the excess energy, and there are different ways to store it. Chemical bonds are, of course, very high energy density, require low volumes, but other ones will require increasingly higher volume. There are interesting opportunities. Pump hydro is wonderful, but there are not that many locations that we have a river and a mountain where we can create a lake. Compressed air, both onshore and offshore, tries to emulate pump hydro in different ways. But I think that we shouldn't anchor ourselves too much to that. For example, if you are in a desertic region, then the best way to use the excess energy that you may have at certain hours of the day is desalinate water. You'll need it. So you do not need to have a standard energy processes like the ones I had just described. And all these systems, because it is daily storage, means a large number of cycles of all forms, temperature, stress, pressure, etc. And we have to recognize how geomaterials will respond. Throughout all this, the theme of mining is playing a critical role. In fact, mining and the availability of minerals is the bottleneck for the energy transition. Example, copper. We need so much copper to upgrade the grid that we would have to open a new mine the size of the Escondida mine, which is in Chile, the largest copper mine in the world, every year for the foreseeable future, for the next 30, 40 years. One of these mines fully operational every year. A new one. Lithium, it will increase 40 times demand. Rare earth elements, 3 times increase by 2040. And plenty of geotechnical issues from excavation, the geoenvironmental, the tailings, the restoration are typical, classical geotechnical issues. Just to give an idea, this is the Escondida mine. The diameter here at the top is about 4 kilometers. So that is 2.5 miles. And the depth is 2,000 feet. Quite impressive. One of the bad enemies of mining is that it's very highly energy consuming. I hinted that at the beginning. In fact, only probably 1% of the energy that we consume in a ball mill is actually used to grind the material. The rest is lost in energy losses. Great opportunities for us for comminution and the improvement of processing of mineral mine components. Once again, I remind you the instabilities that we have seen in fly ash, a similar one, the maintaining in Brumadinho, and other ones that have occurred since. And I am reminded of Jim Mitchell telling us, let's be careful, soils are not inert. With that in mind, we're finally coming to at the end of this presentation, and there were two parts. One was to try to disentangle, analyze this complexity of the energy situation. We realized that it's a huge problem. The change is coming, but not fast enough. So let's figure out how to adapt. Fossil fuels will remain the integral part of our energy system for the foreseeable future. Be careful with words that really are not true. They are not real. They are just sales arguments. If you get lost, go back to this simple relationship. $1, 1.6 kilowatt hours, 0.34 kilograms of CO2. It's not that we are running out of technology. Probably the most important thing is that we share our values, that we have a collective will, and we have a long-term commitment to make it happen. Energy geotechnology, as I showed you in the second half, everywhere of the energy system, everywhere there is a role for us to play, from coastal geotech and mining to the direct components of the energy system. And they all go back to really fascinating thermo, hydro, chemo, biomechanical coupled processes. And nowadays, we have 20 plus 30 years of experience with algorithms and with experimentation to address them. So let's be part of the solution. These are just two pictures of various stages of the group, but just to say what an amazing group. I've been so lucky to work with so many bright minds, and credit goes to all of them. And of course, to the Geo-Institute for inviting me to be part of this, for this effort. Brad and his team, you all know they are amazing. And Maud, I wish the best to the young generation in the Geo-Institute. Thank you all.
Thank you so much, Professor Santamarina, for this excellent presentation. I think we all learned a great deal. Now we are opening the floor for the questions. Audience, if you have any questions, please submit your question in the chat box. Yeah, please. I think I can see one or two questions in the chat box. So while the audience is taking a moment to think their questions, I would like to ask a quick question. So many of us here are students or in early career engineers. So what advice would you give to young engineers who are concerned about climate change and want to make a meaningful impact through geotechnical engineering?
Wonderful. In fact, the presentation today is really directed to you guys. My generation already made a mess, but you will be at the prime of your career in 2050, right? And so please do get involved. Remain thoughtful about it. When you look into your thesis and the classes that you take, do gravitate to courses that have content that will help you develop the foundations for the future of your career. I mentioned politics. We are not educating our students to become involved. There is a huge role to play, a huge. Let's get involved. So I would say, one, I don't want to leave any apocalyptic idea. I don't want to be a negative seminar. On the contrary, remain positive. We, all of us in this community, will do very well because we have the resources to adapt, by the way, by education. We are mobile, right? So that's not the issue. The issue is how can we come all together to build a better world? So educate yourselves and become involved.
Thank you so much. Thank you so much for these insights. I think the very first question I would like to ask you from the audience that did you know that peatlands and mangroves or salt marshes can capture the 5 to 8 times more carbon per meter square per year than a forest?
Yes, in fact, while I was in Saudi Arabia at KAUST, by the way, camels love mangroves, and so you have to protect them. And so they were specifically protected, and they have a root system that makes them indeed very effective for CO2 capturing. So there are in many countries around the world, there are lots of efforts to preserve the mangroves and, in fact, to promote their growth. Thank you for the comment and observation. Very correct.
Thank you. I think we have a few more. So the next question is alarming to hear that we should abandon that idea to be carbon neutral in 2050. What is realistic time frame and would be the best course of action to at least try to get there ASAP?
Yeah, first of all, no, we must not abandon the idea. No. Please remain focused. Don't lose your compass. We have to move in that direction, but also let's be realistic of the magnitude of the problem. And that magnitude of the problem should give us two things. First of all, the drive to invest more resources to make it happen. And on the other hand, the humbleness to realize how are we going to approach the situation. I think that it was buried in one of the slides, but let me just add one point. Globally wise, we are spending about $2 trillion a year in armaments in the military budget. This is about the same budget for carbon capture and storage annually that will be required. So it's not that it's not that the world is running out of resources. We have to think what are the choices that we're going to make. So let me once again emphasize. In no way I try to suggest that we should abandon that as a goal. Is that goal is not happening in the big picture. It's going to happen in subsets of the various economies that were mentioned. I don't know, the oil companies, if they are saying net zero, it's not that they're going to be net zero, it's they're going to be probably running their pumps with solar, or the cities illumination, subsets. Let's don't buy that as a saint behavior. Mm-hmm.
Okay, so I think the next question we have, so does the carbon dioxide emission numbers account for the global yearly massive fires as well as impact on wars?
That is a very good question. And once again, those are some of the numbers that earth scientists and climatologists have to balance out, right? And these are very big numbers, volcanoes and fires, and by the way, fires are getting quite significant. Historical perspective, I'm not quite sure any worse, but the extremes are becoming more common, and then the Arctic regions are becoming exposed, and methane is being released, and methane is worse than CO2. So to do the whole carbon budget, it becomes indeed very complex. So my numbers were only numbers related to our energy consumption. I did not take into consideration all the other factors that come into the picture.
I think we have like 2 or 3 more questions. Thank you so much for answering all of these questions, Professor. So I think the next question is, how will emerging technologies such as digital twins and AI transform energy geotechnics projects?
The next presentation, if I recall correctly, in this series, the next conversation in this series, I will explore this incredible paradigm shift that is taking place of AI. And so in this context, it's also going to play an important role. Just a brief note, last week on the news was the fact that one professor from Berkeley, Yagi, one of the he developed metal organic frameworks, MOFs, Nobel Prize awardee. He won the Nobel Prize last year, and he has just moved to China to lead in Tsinghua University to lead a new center on the acceleration of material designs using AI. This brief announcement I just made, this brief comment, has several connotations. The one that is relevant in this context is the fact that major initiatives are taking place around the world, from DNA to neurology to material science, on accelerated developments using AI. In our field, probably the efforts are significantly minor, smaller than those. But I think that there are great opportunities to improve our geotechnical field, geotechnical engineering and design, using the large databases that we have accumulated throughout the 20th century. So we didn't see a major theme at the international conference in Vienna in this regard, but I think that as I go around the country and I hear what is going on, I think that we're going to see a sudden jump in all these efforts around the country and around the world.
Thank you so much, Professor. I think we have a very, very last question I have. The question is, solar is big now. What is the energy expense to make solar panels and associated systems?
That is indeed also another very good question. I don't have the numbers, but I can tell you one thing. 10 years ago, it will require more energy to build a solar panel than the energy the panel will produce in its life. And so 10, 15 years ago, we were on a negative energy budget making solar panels. That has changed dramatically. From the point of view of material requirements, now the solar panels are very thin. You can almost cover your window with a semi-transparent panel and create electricity. The real problem is that the capacity factor is small, it's 10%, 15%. And so in order to have a certain amount of power that you would deliver with nuclear power, which is steady, you will have to have 10 times more installed power to deliver the same power because the solar goes up and down, up and down, up and down. So it's not just the material needs to make one panel. You have to do the analysis in the big picture of taking into consideration the capacity factor and the durability of the project. Is it 10 years versus a hydroelectric project, which is 70 years? So throughout the life cycle analysis, comparing two equal lives, what will be the actual cost? And solar then doesn't do as good as the numbers are being shown to promote solar. That being said, I want solar, so don't misread what I'm saying. But once again, read the numbers carefully.
I think one of the questions from someone's geology teacher, they asked, what world look like 11,000 years from now when oil, gas, and coal are depleted?
It will be amazing.
It will be amazing, yeah. So I think we are done with this question. So I think I have like one more follow-up question from my last question. So if we're looking ahead, where do you see the biggest opportunities for geotechnical engineers to contribute to solving the future energy and climate changes?
Of course, in the energy geotech and the multiple dimensions that I have suggested, mining is, because of our training, mining is going to remain a big one. And in our programs, we don't do enough emphasis on mining in training the next generations. And coastal geotech, I think that there are so many wonderful opportunities there, near shore and onshore, but coastal. There will be wonderful opportunities to have meaningful impact.
So yeah, thank you so much. Thank you so much again, Professor Santamarina, for sharing your expertise and insights with us today. Yeah, I would like to thank everyone for attending this session. Now I'm just giving the mic to Brad. Thank you so much for having us.
You guys did a great job today, Carlos. That was a fantastic lecture. And for all of the viewers out there, if you do want to go back and watch Carlos's 2014 Terzaghi lecture, you can do that right on our YouTube page. Just Google 2014 Terzaghi Santamarina or something like that. Click the link and boom, you'll watch the original lecture that he gave today with, without all the amazing updates and the benefit of the additional 12 years that he's had since that initial lecture. I want to say thanks to our viewers, especially those who asked questions today. That's what really makes these sessions vibrant, what makes us love doing these live streams is the interaction that we have with you. So a big thanks to all of our viewers today. Mode, great job moderating today. That was fantastic. Carlos, again, fantastic lecture. Our next live stream, I put it in the chat, is in 48 hours. We're going to be back with our publication series that's called Books Rock. Rock, get it? And we'll be talking with Dimitrios Zekos and Tim Stark about their volume on the 2021 Rat Creek embankment failure in California. So you don't want to miss that. You can register free for that at our Eventbrite page and all of our other upcoming live streams as well. Again, if you liked what you saw, like, subscribe, get notifications. We would really appreciate it if you do that. It makes it easier to find the video in search results. And I think that's all I have to say. Our producer today was Aurora Flieger, and we will see everybody really soon with another Geo-Institute live stream.